Okay, so this is section 2 of chapter 9. Section 2 is called Understanding Interest. We're going to do a lot more than understand interest in this section. We are going to calculate a bunch of different types of interest. So the goals for this section are to understand, we're going to want to understand and calculate several different types of interest. Simple interest, so-called simple interest. Okay, we're going to want to understand and calculate compound interest and understand and calculate. These are the goals for this section. This is a long section, that's why I kind of want to lay out the goals, kind of keep us on track here. Since it's such a long section, I'd like for us to have kind of a roadmap. Calculate continuously compounded, which is a type of compound interest, but it's such a special type that we want to consider it separately. Okay. We're also going to want to understand the difference between annual percentage rate, which I will denote as APR here. Now I'm going to officially write down and define these terms, but I'm going to use their abbreviations here. Annual percentage rate and annual percentage yield, which you may have seen these before if you've seen commercials that describe like loans or something, or car commercials. You know, you'll usually see these in the fine print at the bottom of the page where they're describing all of the loan for the car. So you've probably seen these abbreviations before. So these are the goals for section 9.2. So let's start off with understanding and calculating simple interest. And let's really start off with defining what interest is, just in case you're not sure. Interest, textbook definition here, is the amount charged by a lender for borrowing money. Okay, so if you take out a loan from a bank, presuming that with the assumption that they say that it's okay that you can get the loan and everything, that you qualify. Okay, sorry, I'm going to have to repeat that because I got interrupted here. So let me try to retrack where I was. Okay, so interest is the amount charged by a lender for borrowing money. So if you take a loan out from a bank, they approve you for the loan, they give you the money, but they're going to charge you for borrowing the money. Okay, and that charge is called interest. Or if you have a savings account, then you can think of yourself as the lender, lending money to the bank, and they give you earn the interest on the savings account. So interest can be used to talk about what you have to pay for a loan that you may have taken out, and interest also can be used to describe the money that you earn on a savings account. So interest is not necessarily a bad thing. So let's define a few more things here, just so we can all be on the same page when we're talking about these things. The sum of money, or the amount of money that we are either borrowing or putting into the savings account, is called the principal. So the principal is the sum of money on which interest is charged. Okay. Nothing crazy going on here, right? We're just defining these words so that when we build equations out of these, which will be, the goal to calculate interest, we need to be able to know, which number is playing the role of principal versus interest versus rate, which will be the next one. The next definition is the interest rate. The interest rate is the amount charged to the borrower expressed as, how is an interest rate expressed? As a percentage. A percentage of what, right? Because anytime there's a percentage going on, you got to know what is that denominator cut out of, right? Where is this percentage coming from? What is it relative to? And it's a percentage of the principal. So if a bank charges you 5% interest on a loan, that means that 5% is based off of the size of the loan, right? Based off of however large the loan is. Okay. Okay, so now we have the APR, the annual percentage rate. APR is the yearly interest rate. That is charged for borrowing. Okay, so APR is the interest rate based off of interest gained for a year. Okay, now we're going to look first at simple interest. Now that we've got these definitions out of the way, looking at simple interest first, and here's the key thing for simple interest. Simple interest calculations consider only the principal amount. And you might say, well, what else would they consider? So I'll say parenthetically, as opposed to considering interest on, I'll say it this way, interest on interest, which I will discuss this idea more when we move into compound interest. So there is a type of interest that we will need to discuss called compound interest, where you've got some lump sum of money, then some interest is added to it. Like, let's say for a loan, you owe some amount of money, then interest is added on, right? Next time interest is added on, it's taken out of that new larger lump sum of money, right? So now you owe even more interest because it's interest on top of the interest that was already there. Okay, that's compound interest. So I'll go into a little bit more detail when we actually get to that. But for now, the only reason I'm pointing this out is so you understand why the kind of interest that we're about to talk about is called simple interest. Simple interest does not stack interest on like that. Simple interest calculations are only based off of that initial amount. And the formula for it is I for interest equals PRT, where P is the principal, R is the APR, the annual percentage rate, and T is time. There we go. Principal, interest rate, and time. In years, this is measured in years. Principal, of course, is measured in dollars. Interest rate is a percent that anytime you do calculations with, you need to change to a decimal. Of course, we learned that in chapter 4, right? Where we learned about calculations with percents. And I is the interest. So I is the interest that gets calculated based off of this principal. It's not the entire combination of the principal plus the interest, right? If I wanted to write that, I might write it as like some amount, A, is equal to my principal plus the interest, which is PRT. So you might want to say total amount is equal to P times 1 plus RT. That's just this equation, right? Pulling the P off of both of these. So this is principal plus interest. That's what I'm doing here. Principal, P, principal, plus interest, which is PRT. Oops. PRT, right? That's interest. Interest is PRT. So I'm doing principal plus interest. That would be the total amount. So sometimes a problem might say find the interest on this, principal for this interest rate. Or it might tell you to find the entire amount after the interest is added on. So that's all that's happening here. This is the interest, and this is the amount after the interest is added on. And all I did here was manipulate this equation. The reason I'm writing this down is it's going to look very similar to the way compound interest is represented. Using the same letter, capital A, and I'm just trying to connect it to those, to that compound interest formula that we're going to look at in a little bit. First, let's do some examples with this simple interest. Determine the simple interest that is accrued, that just means like earned, right? The interest that's gained on the account for $5,500 for 5 years at a rate of 8.5%. Okay, so we have everything we need. It specifically asked for interest, not for the total amount after the interest is added back on. So that's just a small thing to note here. They only want interest, not the actual total. Okay. We might get the total anyways, just for a little bit of extra practice. So let's see here. First things we need to do is identify these variable letters. P is clearly the principal 5,500. R is going to be 8.5%, which of course need to write that as a decimal, so R is equal to 0.085. Just dividing your percent by 100 to turn it into a decimal. So this is what gets used in our calculations. And then T is 5 years. I is equal to PRT, which is going to turn into I is equal to 5,500 times 0.085 times 5 years. And this is an example of how simple interest does not keep recalculating interest. Like each year, it's not stacking on more interest. It's just straight up based off of the principal, the interest rate, and time, but not stacking interest on interest. And you may not see that necessarily in this formula, but you will see the difference in the next formula. And just trust me for now that this is what this is telling us. This formula, just being able to multiply these things all together, what it's telling us is that interest is not being stacked on top of interest in this particular problem, or for simple interest. Okay, the answer is about approximately, I'll say dollars because it's a dollar amount. I'll make sure I round to the appropriate place, right to the 100th place. So $145.68. Oh wait, no. That is a... No, sorry, that's way off. I'm looking at the wrong solution. I'm following the textbook solution. That was the wrong example. I was about to say, that's kind of low. Kind of a little bit low for a principal that high and a time span that long. Here we go, $2,337.50. Still rounding to the 100th place because it's a dollar amount, right? And for American currency, we don't go past the 100th place in the decimals. There we go. So make sure you can pop this into the calculator and get this answer. So this means, now I'm going to go a little bit further in this problem. This is all the problem wanted, right? But this means, how much would we owe if this was a loan? Let's just say this was, let's be a little bit more optimistic. Let's say that this is an amount we put into a savings account. How much money would we have in our savings account? This much? Well, I would hope not, right? Because we put in 5,500. So how do you find out how much money you would have in your account? If you plop this much money into a savings account with this interest rate and you wait for 5 years, you go look at it, you know this is how you calculate the interest because it's a simple interest savings account. How would you find out the amount of the total money in there? You would add it, right? You would add what you put in there plus the interest that you earned. So you would have approximately $7,837.50. And this is coming from interest. Well, let me say it the same way I said it on the other page. Principal, this, right? Plus interest. So you could, if the problem asked for the total amount in the account after 5 years, if they wanted this number, you could use this formula, right, to get straight there, which I'll show you. It does that. If we look at the calculator, P is 5,500, and then parentheses 1 plus R, which is 0.085, and then times T, which is 5, then close my parentheses, and there it is. It does it for me all at once. It just depends on what the problem is asking for, right? If the problem is specifically asking for interest, then only find the interest. If the problem is asking for the amount total earned in the savings account or total owed for the loan, then you can either do it in pieces by finding interest and then just adding it back, like doing it manually, or you can go straight to this formula and plug everything in. Okay, it's just a matter of preference. You know, do you like to memorize formulas and use them, or do you like to do things in pieces, like more of a algorithmic kind of point of view? You know, just your preference. Okay, so now I'm going to go into example 2, still doing simple interest, just a slightly more complicated and realistic problem. This is example 2 in the text, so what I'd like you to do is pause the video and just trying to show you what it, well, I can't fit it on my desk here. I'll read it to you. It's example 2 in 9.2. I'd like you to pause the video, go open your Hawks textbook, just to save me from writing down this problem. It's like a whole paragraph, right? But I will read it to you right now. Ian is purchasing a new television with a deal from Big Screens R Us. The deal offers 90 days, same as cash, to make the purchase. So what does that mean? Well, they're going to tell us. This means that at the end of 90 days, if Ian has paid off the cost of the television, he owes no interest charge. Okay, so basically this means like they give you 90 days to pay it off. And this seems really nice, right? You'd say, why would a business ever do this? This seems like a terrible business model. And maybe not awful, because you're still going to get your money, but you have to wait 90 days. Well, here's the the point. This is why they do it. If Ian does not pay off the amount, he will owe simple interest for the original purchase amount calculated over the entire 90 days. So what that means is that as soon as he buys the TV, interest starts getting calculated every day. Well, not stacking on, but it from day one, that's when the interest starts to be calculated. He won't have to pay the interest as long as he pays the TV off before 90 days. Okay. Now here's the question. If the price of the television is $2,650, tax included, with an annual interest rate of 21.99%, how much would Ian owe on the 91st day if he made no payments during the first 90 days? So, let's write down some numbers here, and then we'll talk about it a little bit more. The principal, P, is going to be $2,650. The interest rate is huge, 21.99%, which let's go ahead and get that as a decimal, 0.2199. Right, just pop that into the calculator, divide, oh goodness, there we go. Pop that into the calculator, divide by 100 to get it as a decimal. And T, we'll think about T. Okay, let's think about T, because T is measured in years, right? But we're talking about like 90 days, so we'll think about that. So let's just leave that as a question mark or a blank for now. But before we think about time, let's just consider how, first of all, this is an awful interest rate on a purchase. I mean, that is so high, right? That is such a high interest rate. So this is why businesses might do something like this. Because if you pay it off in 90 days, they don't lose any money, right? You still pay them for the TV. You're happy because you were able to wait until you could get your next paycheck to pay off this TV because you had 90 days or whatever. So everyone's happy, no problem, right? But for the people who don't pay it off in 90 days, maybe they forgot, or something came up, whatever, like they can't pay for it within the 90-day period. On the 91st day, they're going to have to pay a whole lot of interest, because the interest doesn't start on the 91st day. It already started at day one. And then all that interest that's been earned through those 90 days, suddenly they're going to have to pay that on top of the price of the TV. So it's very sneaky. It seems nice, right? It seems like the company's being nice, but no one is being nice when the interest rate is that high. Okay, that is very sneaky. All right, so now we needed to figure out what this time should be. Well, I'm going to do it in purple, some side work to determine time. Well, since the interest is incurred over or earned or gathered over the whole 90 days, we have to ask this question. This might seem like a weird way to ask it, but how many years is 90 days? Well, of course it's 0, right? 0 years, but not really 0 though, right? It's some fraction of a year. 90 days is 3 months, roughly, right? Let's just say 3 months. And 3 months is what fraction of a year? So T is going to be a fraction. That's okay. Time can be fractional, right? It's fine. It's less than a whole year, but that doesn't mean you earn 0% interest, right? Or 0 interest, right? They're still charging you interest. It's just on a fraction of a year. 3 months is how much of a year? Well, it's 3/12 of a year, right? Because there are 12 months in a year. So T is equal to 3/12 or 1/4. I'll write it in. Here we go. There we go. So anytime you've got some time span given in months or even days, you've got to convert that to years. Okay, you got to convert that to years. Now, if you know about canceling units and stuff, like some dimensional analysis type stuff, you might like to do it as, you could do it this way. This is a more formulaic way, I guess, of doing it. 90 days, and then times, so you want days to cancel, right? You want days to cancel, and you want to get to months. Well, there is 1 month in 30 days, approximately, right? Days cancels, 90 over 30 is 90 over 30 is 3 months. And then 3 months, I'm just showing the unit cancellation. If you've learned to do things this way, you want to get to years now, and you want to get rid of months. Well, there's 1 year in 12 months, so multiply across, these months cancel, and you end up with 3 over 12 years, which of course is 1 over 4 years. Okay. So time is going to be 1/4. So for this problem, I is equal, no, wait. What did they ask? How much will Ian owe on the 91st day if he made no payments during the first 90 days? So he has not paid any of the TV off, right? So he's going to owe not only the full interest, which I'm about to calculate right here, he's going to owe the price of the TV plus this. So I could go use that formula, like I told you, does it all at once, because that's what they want to know in this problem. They want to know the total amount of principal plus interest, the price of the TV plus the interest earned over the 90-day period. I'll do it in pieces though, okay? I'm just going to do it in pieces so we can see the interest, see how much interest it is. Let's see, where am I? Okay, PRT, so 2,650 times 0.2199 times 1/4. This is giving me $145.68. $145.68. So the total amount then, the total amount, A, is equal to the principal plus, or the price of the TV plus the interest. And for us, that's going to be 2,650 plus 145.68. And then that's going to give us, so on the 91st day, this is how much he's going to need to pay. For the TV. Okay. Okay. We have done simple interest, understand and calculate simple interest. We did a couple problems. Let's move into now this compound interest stuff. All right. So, the book says, beginning the compound interest part of this section, each of the previous examples was based on the use of simple interest. For certain types of loans, interest is calculated and applied more than one time per year. This is known as compound interest. So, to me, that's not a great explanation of the real difference between compound interest and simple interest. The real difference is not that it's about the number of times per year necessarily, though I guess that's one way to say it, but the point is that the interest is calculated on top of interest that was already earned. So I'm going to say it like this. Oh, actually, I see. They say it a little bit better in their little box where they officially define it. Yes, this is much better. Compound interest is interest that is computed based on, now, simple interest was interest that was computed just based on the principal, right? But compound interest is based on both the principal and what? And what else? The interest that was already gained, so the accrued, I always have trouble saying that word, interest as additional, principal at each interval. Oh my goodness, at each interval. Okay, so there's a bit more to say in this definition. I'm going to leave a little bit of space. We have a formula coming too. But just to give you an idea of what's happening here, say you've got some amount of money that is in a savings account, right? So some sum of money here represented by a circle, and then you gain a bit of interest on it, right? You gain a bit of interest, little bump of interest. So now your money is a bit bigger, right? In the next stage here, your sum of money is a little bit bigger, right? Because it's the original sum plus that little green interest bump, right? Now, interest is gained again, but not the same amount of interest, because now the interest is based off of the new principal. So this is the new principal, which is larger now because it has interest. Hence, the interest that you earn on this larger amount becomes slightly larger. It's a slightly bigger bump. Okay, and then now, maybe you already can kind of see how each step it's going to get bigger, right? Now you have even more principal, so the interest earned on this new principal is even bigger, right? Okay. This is the power of compound interest. So yeah, I think hopefully you can imagine just how powerful this can become. So this raises a lot of interesting questions like, well, if we compound it frequently enough, do I earn like infinite money, right? So to be able to answer these interesting questions, or that interesting question, let's get a little bit more down about the definition. Let's write the formula down for this stuff, and then we'll start investigating. Okay, so here comes the rest of the definition. The future value is just what I've been calling the total amount. So the interest plus the principal that's already there, that's what I've been using capital A for total amount of money. They use capital A as well. Total amount of money, A, an annual It's a long definition. Okay, So before I write the formula officially, let me read this definition. So compound interest is interest that is computed based on both the principal and the interest earned as additional principal at each interval. So what are these intervals they're talking about? Well, the intervals are going to be the n compounding intervals per year. So that means how many times does it compound the interest? Does it only compound once a year? Right? Does it compound twice a year, semi-annually? Does it compound monthly, 12 times a year? These little arrows I drew, each one of these little changes from here to here, here to here, that would be representing a compounding interval where it recompounds, right? Where the calculation is done again. So how many times does that happen per year? Well, that's denoted by this letter N for compounding intervals that happen per year. So there are different common ones, like annually would just be one compounding per year. Semi-annually, which would be twice a year. Quarterly, which is 4 times a year. Monthly, which is 12 times a year. And daily, which is 365 times a year. And I guess weekly, you could say weekly. Yeah, why not? Weekly, which would be 52 times a year. So you may think, you probably are thinking, the more number of compoundings, the better. If we're talking about a savings account, right? If it's a loan, then the more number of compoundings, the worse, right? I like to take the point of view of thinking of a savings account, though, to be a little bit more optimistic. Now, what is the formula? It's going to be, first, principal. That makes sense. Principal needs to be involved. The original principal. And then we have this weird relationship with 1 plus r over n, where n is that number of compoundings, all raised to the n, that's the number of compoundings again, times t for time. So it's an exponential relationship because the variable t for years, the number of years, is up in the exponent position. And time, if we wrote this as a function, time would be the independent variable here. It's an exponential relationship, meaning that each gain is gaining speed, right? The gain from here to here is smaller than the gain from here to here. Like each gain is getting larger and larger as we go on. Okay, so a very powerful type of interest. So one thing to note is that just looking at the formula here, they did not give us a formula for specifically the interest, right? Because this is the total amount A. That's why I like to give you the formula for total amount based off of the simple interest from earlier, because that's the deal with the way that this function, or rather this formula, is built. It would be weird to get the it'd be a little bit more algebra than we want to get into to be able to explicitly write down a formula for the interest. For us, if we want to know the interest and not just the total amount, the easiest thing for us to do would be to calculate the total amount and then subtract the principal to figure out what the interest was. And that's how we'll do it if we're asked for it. Okay, so that's just something to note, is that there is not explicitly a formula for interest, for compound interest. This formula does all the work all together for calculating interest and combining it with the principal. So what I'm saying is, like, this formula does not tell us what this little green bump would be. It tells us what the whole orange thing would be after the green bump is added. Okay. Let's do an example. Example 3 from the text. This is a short one, I'll go ahead and write it. It says, Lily deposits $12,000 into a savings account, into an account with an annual interest rate of 4.5%, and let's say that it compounds, so it compounded monthly. If she leaves the money alone in the account for 10 years, what will the future value be at the end of the 10 years? Okay. P is $12,000, so I'll just write 12,000 without the unit there. R is 4.5%, which I need to remember to write as a decimal. N, the number of compoundings, is monthly, so N is 12, because N is the number of compounding intervals per year, and if it happens monthly, that means 12 times per year, and T is 10 years. Have everything I need. A is equal to, I'll just rewrite the formula for reference, here it is. Okay, that's giving me A. So the total amount, again, this is not going to give us the interest earned, it's going to give us the interest earned plus her original principal. Okay, all right. So 12, which is exactly what this problem asked for. So we won't have any extra steps to do at the end. 0.045 over, gotta make sure I don't mix up the T and the N, right? So 12 and then 12 times 10 up in the numerator. I mean, no, not the numerator, the exponent position. So A is going to be equal to, or I should say approximately, because I'm going to have to round, and I'll show you how to plug this into the calculator, or at least into my calculator. Might be a little different for yours. We're going to say 12,000 times, and then parentheses, 1 plus 0.045, divided by 12, close parentheses. So now I'm here. Now I'm going to hit raise to, so that little raise to, the exponent button, open parentheses here, and then 12 times 10, and then close parentheses. It is absolutely necessary to write parentheses around this with that multiplication in the middle, because otherwise the calculator thinks you just want to raise it to the 12th and then multiply the whole thing by 10, which is not what we want to do. Now, alternatively, if you wanted to just say raise to the 120, that's fine too. If you already, you know 12 times 10 is 120, and if it's just a single number up there without the multiplication, then you don't need parentheses around it. Okay, but I'll leave it as 12 times 10, closing in parentheses, and we're getting that, which is, I need to round appropriately, so I'll say $18,803.91. So, this is the end of the problem. That is the future value for the amount of money that she will have after 10 years in this account with this interest rate compounded monthly. How much interest did it earn then? So if I ask this question, how much interest was earned? Like, how much did she earn just by having the discipline to be able to leave that money alone for 10 years? How much interest was earned? How much did the bank give her? All we would have to do is take that 18,000 blah 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 and subtract her original amount, right, which would give us that 6,000 whatever, it's nearly $7,000, $6,803, right, 0.91. So again, this formula does not explicitly give you the interest earned. If you want to just know the interest that was earned, you got to do this extra step where you take the total future value or the total amount and subtract the principal back out to find out how much interest was earned over that whole 10-year period. But to be honest, the question that you're in your real life, the question that you are going to want to answer more likely is going to be this question, right? How much money will actually be in there? It's kind of interesting to know how much interest was earned, but that's just kind of a bonus thing, right? In the real life, you're going to want to know how much money is going to be in my account, right? That's the more direct question. And we have a formula right there for that. So now we get into, now that we've done a problem, just seeing how this calculation goes in the calculator and everything, now we can investigate this issue of, is more compounding better? And is more compounding so much better that I would always want to go for higher numbers of compoundings versus higher interest rate? So now I'm going to get into a question, and I might even make up a question if the book doesn't have one. Yeah. Let's compare some savings accounts. So I'm going to make up an example now. Three, four. Not from the text. And I'll just say, which is a better savings account? Which will give you more money? And I'll say savings account A. And let's say that the what is going to be different for different savings accounts? Well, not the principal or the time, right? Because you determine the principal. You determine how much money you put into the account, and you determine how long it stays there. What they control is the number of compoundings and the interest rate. So let's say this savings account A has an interest rate of 8.0%, and N is, let's say it compounds quarterly. So we'll say N is 4, so this is quarterly. Okay. So maybe these are two different banks, right? Okay, now this one has an interest rate of 6.0%, but N here is daily. So remember that picture I drew, and you might be thinking, as you remember that picture and think about what it means for these things to be compounded, you might say, wow, that is, if you just glanced at this, right, you would say, wow, that has got to be way better, right? Daily compoundings, that means every day, every single day, they recalculate your interest, add it back on, and then the next day they recalculate based off of that higher amount, and then they add the interest back on. So at a glance, you may say, this seems way better. But let's investigate. Let's make up a calculation here. Let's say, so if I'm asking you this question, which is a better savings account, and I only give you this, that means you have to pick some principal and some time span to be able to compare these. Okay. If the principal and time is not given, then you have to make it up. But see, the thing is, it kind of does depend on how long you can save the money, because time span, the span of time might be, you know, this one might be better on a long term or short term versus this one might be better on, you know, the short or long term. So I think if this problem came up on a test or on the homework, they would have to give you a principle. They would say like, oh, Susan is saving money, you know, and she has $5,000 for 6 years, which is a better savings account, right? So let's just make something up. Let's say that you have a principal of $1,400, right? Your stimulus check, and you want to save all of it. and you want to just leave it in that you don't need it right now, right? So you're just going to try and leave it for like 10 years. Let's let t be 10. 10 years from now, you're thinking about maybe you might buy a house at that time. If you just dropped this in there, you know, and you're trying to compare banks, which is going to give me more money that I could put towards like a deposit on a house, which, to be honest, you know, you'd probably want to save more than that. But anyways, let's just use these numbers to compare. So let's say savings account A. So go ahead and run the calculations yourself and see what you get. And I will do it as well. So A is equal to P, which is 1,400, times 1 plus R, 0.08, over N, which is 4, raised to the 4N times 10 for time. So remember, you got to convert R to a decimal. Can't forget to do that. So I've got 1,400, 1 plus 0.08 divided by 4, raised to 4 times 10. Okay. Ooh, where did my marker go? So I'm getting approximately $3,091.26. Okay, good. What about savings account B? Same principle, different interest rate, and different value for N. Same value for time, though. So 1,400, and then I'll change that to 6 divided by 365. Oh, I'm going to close parentheses, raised to 365 times 10. Aha. $2,550.84. Clearly, savings account A is better. I'll redo it just in case you don't believe me. 1,400 times 1 plus 0.06 divided by 365 raised to 365 times 10. There it is. I'll redo the other one too, just to show 1 plus point divided by 4 raised to the 4 times 10. All right, so I did my calculations right. I did them both twice, got the same answer. So what's going on here? So what's going on is that compound interest, while it is very powerful, it does not mean infinite money, okay? It does not mean infinite money because it reaches a limit for how much it can grow, all right? And that is, that limit leads us into a new formula for the so-called continuously compounded interest. But let me say a little bit more about this from the point of view of like real life. You know, I don't have like, still not in the position where I can be in this situation where I'm comparing savings accounts, right? But I can say just based off of what I know about how the math works, that my rule of thumb for you or some advice to take would be to, in your decision, weigh the interest rate more heavily, much more heavily, than the number of compoundings. Because the number of compoundings, the more is better, right? If the interest rate's the same, more compoundings is better. But it doesn't make up nearly as much of a difference as a small change in interest rate can. And actually, this is a huge change in interest rate, really. If you've got a savings account, no matter what the compounding is, 8% versus 6%, 8% is going to be better. Savings account interest rates matter much more. than the number of times they're compounded. Unless it's just, if the difference was like 6% versus 6.2%, then that would be much closer, and we'd really want to do the calculation to really make sure. But I think as a general rule of thumb, you should consider interest rate to be a more important factor in a decision like this than the number of compoundings. So what I want to do is investigate the why, see if we can see why interest rate, or rather interest earned is not approaching like some infinite number as number of compoundings increases. So let's investigate let's say compound interest as n, the number of compoundings, gets very large. Okay, so what I'm going to do is I'm going to pin down some principal, some time, and some interest rate, and then I'm going to play with the letter n, make it get larger and larger and larger, and we'll see what happens to the calculation, to the future value, to the total amount in the account. So let's let P be, let's keep things easy. Let's let P be 1,000. Let's let R be 5%, and let's let T be 5 years. Okay, and N I'm going to be adjusting, right? So N is going to be changing, and that's what I'm going to be investigating here. So first, let me say, okay, let's do annual. So this is for N equals 1. So I'm going to have A equals 1,000 times 1 plus 0.05, that's my rate, R, 5%, over N is 1, raised to the 1 times 5. Okay, that is going to be some amount. Give me a minute, let me write them down. Let me write down a few of them, and then I'll go do all the calculations. I'm going to jump from annual to, well, no, I won't jump. I'll do semi-annual. Semi-annual means N is going to be 2. By the way, all these annual, semi-annual, weekly, monthly, quarterly, all of that is on a table in page 474. And they tell you what each of those words means and what they mean for the value of N. So notice everything is staying fixed except for the value of N. See, everything's staying the same except for the N, 2. There's 2 for semi-annual. Then we have quarterly. So that position is going to change to a 4 for quarterly. So there's a 4 there and a 4 up here. Okay, I'm going to jump now to daily, just because I don't want to write down all of these. Oh crap, what did I do? 365 times, that's supposed to be 365 times 5. So that's N times T, and that'll be something. And then let me just say, N, what if they did it not just daily, but every minute or something? Let me make N huge. So there's 365 days in a year. Each day is 24 hours. Let me do that. I'll just do hourly, which is crazy. This would not happen in real life. I'm doing this just as an example so we can see what happens when we let N get very, very large. So same interest rate. Now N is going to be that. So that's how many hours are in a year, 8,760. All right, now let's run all these calculations. Okay, so I'm covering them up just so we can look at these one at a time. Okay, so first annual compounding is $1,276.28. Okay, fine. Now, what if it's semi-annual? How much more money do we earn? Okay, 1,280. So about, let me say, the change from here to here, I'm just going to say approximately from here to here, is $4. $4. Just, just approximating. Okay, what if I go from semi-annual to quarterly? Okay, 1,282. So a smaller change in between those two. What if I go to daily? Now, we're jumping from quarterly, only compounding 4 times per year, to 365 times per year. We should expect a big jump here, but what happens? Again, only a $2, roughly, jump. Okay, now what if I go all the way to hourly? What happens? Look at that. A 2 cent, 0.02 increase. Whoops. From there to there. All right. So let me write down for you what's happening here, how we can interpret this. As the number of compoundings increases, the amount earned approaches a limit. Approaches a limit. Okay. In other words, we cannot earn infinite money by taking a lot of compoundings. And why is that? Well, we could really dive into this. It's a very interesting question, and but we don't really necessarily have the algebra tools to really look into this. But based off of the formula, what I can tell you, maybe this will give you some intuition about why this is happening. As n increases, it's in the exponent position. That means it should be blowing the number up as n increases, right? But n is also in this denominator under this fraction here, or in this fraction inside here. So n is pulling up and down at the same time. When n increases, it's making this number smaller because it's in the denominator, and it's also pulling the whole number up because it's in the exponent position. And it just so happens that there is a very particular special number, which again, I'm gonna have to sweep some of the algebra under the table. But if we take this quantity of 1 plus 1 over n raised to the n, so if we just try to investigate, what if we just like ignore the p, ignore the r, the t, let them all be 1, let the p be 1 so it doesn't matter, let r be 1 so it doesn't matter, let t be 1 so it doesn't matter, and we just look at n, and we say, let n get as large as possible, pulling up and down. What happens? This approaches a particular number as n approaches infinity, as n gets huge. And that particular number, as strange as it may seem, is the number e. The number e that you may have seen on your calculator, or maybe you've heard of before. So e is an irrational number. It's approximately 2.718. I say dot dot dot. So I guess if I say dot dot dot, I'll say equals. We won't really approximate it because we have a nice button on our calculator that has it approximates it for us. See, there's the E button. or I'll show you again. So it's on my calculator, it's right up there above ln, so I have to hit second and then that. Okay. Now, how is this going to be used in our compound interest formulas? When n tends to infinity, what does that even mean? Well, at this point, what I'd like to do, because the video is already an hour long, I feel like this is a lot. I'm going to break this into pieces. I'll call this 9.2 part 1 or part A. And then I will pick up with what is going to be called continuously compounded interest. And that will make use of this number e as n tends to infinity. So let me say a little bit more, though, about the point of this, though. The point is that as the number of compoundings approaches infinity, we do not end up with infinite money. We end up with a new type of savings account, and we end up with a new formula. So I'll leave you with a little bit of a cliffhanger there, so a little bit of motivation to watch the part 2 of this video, because in that part 2 I will give you the formula and talk more about this continuously compounded interest.